Dexterity, the ability we have in manipulating objects with precision, is essential in our everyday life. It is also a direct expression of our creativity, and it shows how our brain matures and evolves with time.
Well, dexterity implies manipulation, and manipulation of objects is occurring against gravity. Gravity is acting on the object all the time and has to be taken in account in the modulations of force that you are exerting on the object. But this kind of coordination is not innate, it's learned. And children are learning this process during the 1st year of their life.
For 10 years now, a scientific team led by Jean-Louis Tonnard and Philippe Lefebvre of the Université Catholique de Louvain and by Joe McIntyre of the French Centre National de Recherche Scientifique are studying the mechanisms involved in dexterous manipulation. When holding an object between two fingers, the grip force creates a friction with a resulting force called the load force, which compensates the weight of the object and prevents it from falling. If we loosen the grip force decreases, and as weight remains constant, the object falls. When manipulating an object, the acceleration we give to it modulates the load force, and the grip force varies synchronously to the load force. This allows holding the object optimally, whichever movement is accomplished.
What is really amazing is that the brain can anticipate, and this anticipation is learned. And so our research opened, in fact, the door to, I would say, a large domain of research in the field of how the brain is learning new process, how the brain is learning to control movement in new environment.
And what better challenging situation for the brain than putting the body in a zero-gravity environment? To study this, the team of Jean-Louis Tonnard and Philippe Lefebvre have put together a vast study program. After 6 theses, dozens of scientific publications, and 20 parabolic flight campaigns, the experiments scheduled on the International Space Station represent the culmination of a solid scientific expertise. The setup of the experiment is designed to study the dynamics of prehension, that is, all forces acting on the moving object. These forces are measured with an instrumented device called the manipulendum. It carries a wide range of sensors like accelerometers, gyroscopes, force-torque sensors, and moisture sensors. The setup also allows to capture kinematics of movement in 3 dimensions, by using Kodak camera sensors, recording the trajectories of the LEDs embedded in the manipulendum. The GRIB experiment is replicated in 3 identical sessions on Earth, ensuring that the brain has fully integrated the task before launch. Then, the experiment is replicated 3 times on board the International Space Station, allowing a complete follow-up of the learning in microgravity. A reduced session is organized the day after return to ground, followed by 3 replicates of the full session in the following months.
In microgravity, the weight of the objects is equal to 0. And in fact, the relationship between the kinematics of the upper limbs and the dynamics of the manipulation, the precision grip, is perturbed. And so the question is, how long will it take to the brain to learn these new environments? How long will it take to the brain to relate again the inertia, the accelerations of the upper limb, to the dynamics of the precision grip, of the forces exerted on the object during manipulation? And this is what you want to study.
The GRIB experiment has recently been commissioned on the International Space Station by astronaut Thomas Pesquet. It will provide data that will be useful in understanding tactile sensation, a key element in developing new haptic controls for astronauts. Another application is in healthcare, particularly in cases of patients with cerebrovascular trauma. The revalidation notably involves area of the brain linked to dexterity learning.